Hello to the online world here. It's a pleasure to have Nick Beaumont visiting us from Eindhoven today. Nick has been actually in I think pretty much all the big places in the Netherlands. You've been at CWI, you've been at ABN AMRO and Eindhoven. You're sort of getting the gamut, and Leiden also, right?
Oh, yeah.
Nick has done a good deal of work on multi-party computation, as well as some quantum computation work. If you're interested in that, let's talk later. But in particular, he's going to tell us about work on efficient multi-party computation for algebraic kind of structures, especially, I think, if that's an appropriate description. So welcome. Thank you.
Yeah, thank you very much, Josh. Thank you for having me here. So I will talk about multi-party computation research at the Technical University of Eindhoven. And we are there in the group with Berry Schoenmakers, Frank Blom and Niels de Vrede. So many of the things that I will talk about is joint work with them. The plan for today is to present you MPyC, which is a Python framework developed mainly by Berry Schoenmakers for performing multi-party computation. And this framework is not so much tailored to a production environment, but more as a tool for research and a rapid prototyping environment. And then I will talk about performing linear algebra over the rationals in an MPC setting. And if time allows, I will say something about comparison or secure comparison. But if there's no time and you're interested in that, please see me after the talk. So let's motivate MPyC or MPC. Why do we want to have multi-party computation? I have the following example. Let us suppose that the US Census Bureau wants to compute statistics over medical records. Well, in a world without MPC, the hospitals would have to send the medical records to the Census Bureau, or the Census Bureau queries them, and then computes the statistics that it wants to compute. But with multi-party computation, we can have a better situation in terms of data privacy. Namely, the hospitals can run an interactive protocol together with the Census Bureau so that the Census Bureau gets, in the end, the desired statistics. And by the way, the hospitals and the Census Bureau agree on what statistics are allowed to be computable. However, the Census Bureau does learn nothing beyond this statistic. So let's describe this a bit more formally, or maybe forget the application. Let's just talk about what MPC can do. So here we talk about three parties that each hold a private input. And the parties want to compute some function that takes these private inputs such that no party learns more than what can be deduced from her input and the output of the function. So there is an example. We could be interested in learning the sum of those inputs, or the sum and some product as given there by F2, or maybe even we want to make a comparison. But let's not talk about that yet in this talk. How to achieve this? So multi-party computation comes in two flavors. Garbled circuits and arithmetic secret sharing. I don't want to exhaustively explain what especially the first type means, but I just want to say to the experts or in this field, I want to scope the talk that I only want to talk about arithmetic secret sharing here. Arithmetic secret sharing goes back actually to a paper by Blackley and also a paper by Shamir from the late 70s. And here the question is, how can we share a secret among several players? Well, we can do that with polynomials in the following way. We assume that we work over a finite field. Here I took the integers modulo a prime. and I choose the prime strictly larger than the number of players n. And I choose a threshold parameter, which is an integer, which is strictly smaller than n over 2. And we are here targeting the passively secure case, which means that the parties, they follow the protocol, but still they try to learn as much as possible from all the protocol transcripts. Now we choose a random polynomial up to degree t, such that the polynomial evaluated at the point 0 equals the secret. So you can think of a picture in your head, which doesn't make sense completely because we are here working over a finite field, so the dashed part doesn't exist, of course. But in this way, we could evaluate the polynomial in other points than 0 and give the evaluations, so kind of the y value, to the different parties. And if we evaluate that polynomial at enough places, namely t plus 1 points, then those evaluations define the polynomial and allows the players to, or the parties to reconstruct that polynomial and reconstruct with that the secret by evaluating the polynomial at point 0. And on the other hand, t evaluation points, they don't give any information about the secret, so this is the threshold property.
Can I ask quickly why you're restricting the threshold to less than half the players? That's something you'll need later, to less than n over 2?
I wanted to make the parameters concrete here.
Okay.
Yeah. So a bit of notation. So I use these double brackets for a secret shared value. So this means that A is from the finite field, and the parties each hold a share of A. And then I can perform operations with those secret shared values. I can perform addition, which is actually a local computation. So there's no interaction required between the players to compute the addition. And there is multiplication, which is more expensive in the sense that now the parties have to communicate to each other. And the reason for this is that if you do pointwise multiplication of a polynomial, then you end up with a higher degree. So you need some protocol to bring back the degree to what you started with. And that requires the communication. So if you want to perform computations with MPC in practice, then it's convenient to have some kind of framework that helps you with implementing all this communication logic and arithmetic over finite fields. So hence there are MPC frameworks, and here is a list of such frameworks. The first one was Fairplay from 2004, and since then there have been several frameworks, and these frameworks are all for arithmetic secret sharing. So there are also garbled circuits based MPC frameworks, but I don't mention them here. And in this talk I want to present to you MPyC, which is mainly developed by Berry Schoenmakers from the TU Eindhoven, and was inspired by VIF, which is also mentioned here in the list, which was from Aarhus University, from Geisler et al. So if we classify MPC frameworks within arithmetic secret sharing, then we could distinguish between library-based frameworks and domain-specific language-based frameworks. So in a library-based framework, the MPC functions are just library calls, and you can mix those calls with or features that the host language offers you. So for example, if you need to compute a Legendre symbol, then you just use the feature provided by some other library, and you can mix that with your MPC protocols. Whereas there are also frameworks out there who offer a domain-specific language, and the latter might be better suited for correctness verification. But on the other hand, if you need something that is already there in the host language, then you first need some way to import that or make it available in your little world with the specific language. But yeah, both approaches have their pros and cons, but MPyC is a framework of the first kind. So let's talk about how MPyC works under the hood, about the execution model. So if I want to compute, say, two products in succession, here the E depends on the value of C, so first I have to compute C, and then I can compute E. If I would do that in a synchronous programming environment, then you basically have to wait till C is available, and only then you can start computing E. And because here a multiplication involves communication between the parties, you have to actually wait for this packet to go out to the other parties, and the other parties do something and then send you the packet back before you can start your next multiplication. So this would be slow. Hence, Viv introduced this, and also MPyC uses the asynchronous model, where you create a task for an operation that would require network communication, and it would immediately return you some object that indicates that you will get that value in the future. And in Python that is called a future, or in some other languages it's called an awaitable, but it's all part of the same idea. So you can build up a computation graph with these futures, and then at the end await the future and get the result. And there's also a notion of coroutines, that you can map these kind of operations on a single thread if you want, or on a thread pool. But the benefit of this asynchronous execution model is that you can already look ahead and see what is coming, and you can already execute local work which you might need in the future. So for example, if your protocol requires a random bit, you might do some, or you might require a pre-computation that you can already carry out. So it's in some sense a hybrid form of greedy and lazy execution. You want to be greedy in the sense that all the local work that you have to perform before sending out a network packet, you want to do greedily, while all the work that would come after the response of your fellow parties, that you schedule lazily. So you can push all kinds of work on the CPU, or you can make or keep the CPU busy, even though you are waiting for network packets to arrive. And there's a question, yeah, please.
Do you also kind of bunch up the network communication so that you have fewer connections sending more data at once?
There's a question whether we amortize network traffic, so whether we combine several things in a packet. Yes, that's also a method that you can use. And I know that Viv uses that for some operations, but MPyC uses that for some operations, maybe not for all, but that is indeed a technique that you can use as well to make things more efficient. But on the other hand, you could also say that a network packet is quite small in itself. So also the operating system does some chunking there. It cuts the stream in packets. So as long as you make sure that you fill that pipe, that stream, then you get that behavior that you suggest already a bit.
Because you have a long-lived connection between all pairs of...
Yeah, there is a long-lived connection between all the parties. Okay. Yeah. So this asynchronous model has these benefits, so that you can keep the CPUs busy. However, you need some way of throttle the computation in the sense that if you would set out all the work that your algorithm is going to require at once, then you might fill up the memory. If this executor goes greedily through your code, say through a long loop, and keeps setting out new work, then at some point you fill up the memory, so you need to throttle there. But there's also a mechanism in MPyC called barrier, which is meant for that purpose. Okay, these were some slides about the theory of MPyC. Let's see it in practice. And for that, I'm going to switch to a different view. So here I am in a Jupyter notebook, and one of the nice features of MPyC is that it can run in a single party mode in Jupyter. And this is maybe a bit counterintuitive because we do multi-party computation. Then why would you be interested in running a single party mode? Well, that is very useful for debugging purposes. So it has the same API, so exactly the same script can be run in multiple instances of Python. And of course you need some small configuration file to tell at which ports those different nodes are listening so that they can find each other. But when you set that up, you can run exactly the same code as in this single player mode. And by the way, if you are in a notebook and you haven't installed it, you can install it by this single line of code, this exclamation mark pip install MPyC. So here I'm going to import the package. I'm going to define a secret integer type. And now I can perform a computation. So I can make a value 3, make a value 5, which are secret integers, and compute the product. And this MPyC output will say that it reveals the product. So I open the result immediately. Okay, nothing happened so far. I created the or Z. I can inspect what the Z means. It's a coroutine object. So that means that here we were greedily, so we returned immediately, but nothing happened. I still have to run that coroutine. So let us do that with this line. And I get the value 15. Okay, now you might wonder what is going on here, because, well, you have multiplied the numbers 3 and 5, and it's 15, I believe that. But where is the randomness here? Because here there's only a single party who inputs 3 and 5, and if you would now copy this instance to, say, 3 parties, it would still be 3 and 5. So the parties would actually share a constant polynomial. So that's not really useful. Well, it is useful for development purposes again, but we keep in mind that this is a simplification. Because if you would really use this in a multi-party setting, you would have to branch on the party ID, and the parties will, of course, input different data, because that's the entire purpose of doing multi-party computation, that different parties have different pieces of information. But again, this is just a nice simplification that we can use to input values, and then we can compute with those values as if we were computing with values that are originating from a single player. Well, another example here is that I can create a secret random field element. And this is happens to be the random field element. By the way, I can inspect in what field I'm working.
So that's X is secret shared?
X is secret shared, indeed, yeah. Here we see that we have a 64-bit modulus. and I can inspect more. I can inspect the bit length of this secret integer, which is only 32 bits. And that, again, seems to contradict each other. But the reason why this bit length, which conveys the usable bit length for the user, is only 32 bits, because we have this headroom that you need for a secure comparison operator. Well, I've got another example here to create a random bit. Well, this is seems to be a random bit. And also here I show an implementation of a protocol that could create a random bit. So here I start with creating a secret shared field element. Then I open the product or the square of that field element. Then I compute the inverse of the square root of that square. And then I multiply x, the original random field element, with this inverted square root, which gives me -1 or +1 at random. And then with this small transformation, +1 divided by 2, I go to 2 bits. I even have here a small example of comparison. So I have two values, 1 and 2, and I want to compare them together, or compare them to each other. And indeed, x is not strictly bigger than y, so I get a 0 here. If I would change the code, then I get a 1. Okay, so this is a small introduction. Let's now go back to the second part of my talk.
While you're doing that, I'll ask, maybe you should answer it later, but why you're doing such a complicated bit generation. Is there really a benefit to that over generate a random field element and take the low order bit or something like that?
The question is why I generate a random bit in this fashion, and do you mean, it's your question, why the random bit function is implemented in the above fashion?
Yes.
Yeah, let's take that offline, because okay. I think there are several random bit protocols, and each of them have some constraints, or like one question is whether you want to have perfect correctness, I think.
Okay.
Yeah, let's take it offline. Yeah. Okay, the next part of my talk will be about secure linear algebra over the rationals. And this is joint work with Frank Blom, Berry Schoenmakers, and Niels de Vrede. And I want to here scope the setting. I'm still in secret sharing based multi-party computation, and I focus on the multi-party scenario with larger or equal than 3 players. And I assume that I have some arithmetic black box at my disposal, which provides me with, say, an addition operation and multiplication operation and opening values, etc. So I don't specify exactly which MPC framework I use. I view it as an API that is there that I can use. And now my problem that I want to consider is that I have a full rank square matrix A and a vector B with integral coefficients, and all those entries are secret shared among the parties. And now I want to solve the linear system AX equals B, so I want to solve for X. And I want to do this over the rational numbers. The rational numbers, to use the correct pronunciation. So what is the motivation here? I view the rational numbers as some kind of approximation to the real numbers, and engineers usually want to solve linear algebra problems over the real numbers, and if they come to the cryptographers and they say, hey, we have some privacy problem, we want to solve a linear algebra problem in the context of MPC, well then maybe the rational numbers are the closest arithmetic structure to work over, which mimics the reals. And we are interested in data processing applications or secure statistics, etc. If we look at the related work, then there is related work by Thomas Toft from 2009, who works over rationals in MPC in the context of solving linear programs. And in the two-party case, there are some references mentioned there, but well, I focus on the multi-party case. If we think about performing arithmetic in a finite field in MPC, and then think about integer arithmetic versus rational arithmetic, well, let's first say that integer arithmetic is easy to do. So we have the correspondence between the integers minus p over 2 to plus p over 2 truncated or floored. And as long as we don't wrap around the modulus, we keep this correspondence. So we can perform additions, multiplications, and it's as if we were working over the integers when our prime is big enough. With rational arithmetic, we could do a division because we are in a finite field, and then the division would be the multiplication by the multiplicative inverse of b. And as long as a and b are small enough, then there is still a correspondence. It's just that if we would look at this field element x, we don't recognize there anything human, right? If you would if you would compute 2 over 3, you get some humongous field element, and with rational reconstruction, you can still reconstruct these numerator and denominator, namely by performing a lattice basis reduction. You encode these the basis as shown here on the slide, and if you run Lagrange Gauss, you will eventually get back a and b. The problem, however, is if you want to perform this in a secure multi-party computation, you must be constant time or data independent. So you would have to run this algorithm for the worst case and pad it with dummy operations. And the worst case was analyzed by Brigitte Vallée. It's order log p iterations, where in every iteration you would have to do an integer division, so division with a truncation. So that would be impractical in multi-party computation. So our approach is different. If we look at the problem of solving a linear system, well, let's just invert the matrix, because we have a full rank matrix, and numerical people would never compute an inverse, but here we are doing exact arithmetic, so we don't have condition numbers to worry about. And you can think about the inverse as the adjugate matrix of A divided by its determinant, where both of these objects, like the adjugate and the determinant, are over the integers. So again, if we have a prime that is big enough, we can embed them in the finite field. So this representation of the solution prevents the occurrence of rational entries. And with that, we don't need rational reconstruction. So here we work over the field Fp. We are going to compute the inverse of A via a modified protocol from Kramer and Damgaard, which is in turn based on Barilan-Beaver from '89. And in this Kramer and Damgaard protocol, which was originally presented for computing the inverse over a finite field, there we keep at all places the adjugate and determinant separate. And P must be large enough so that we don't get wraparounds. And here that's easy to compute. It's essentially the Hadamard bound for that matrix A. And here, or I call the matrix M, where I used the matrix A before. But anyway, it's this B is a bound on the elements of that matrix, and then that's the Hadamard inequality. And the word essentially means here that I still have to compute this product. So then, in order to represent that product, I need to slightly increase P, of course. Well, the protocol goes as follows.
Doesn't that mean that the determinant can be huge?
Yes, the determinant, there's a question here that asks if the determinant can get large or huge. Yeah, that is indeed the case. So we are doing exact arithmetic here, which means that you have an inherent size growth. On the other hand, if you would like to do approximative arithmetic, or say floating point arithmetic, you would have to first build a floating point computation in multiparty computation, which is also expensive. So there's a trade-off there, and depending on your application, you might use this approach. I mean, this works well for small dimensions. And if you have, say, a prime of 200 bits or 1,000 bits, you can still handle many cases. But on the other hand, if you have a huge matrix, there's no way that you are, it will not be efficient because you have this big growth, and you need a huge prime, and making computations with that big prime is heavy. So indeed, there's no free lunch. So the protocol goes as follows. This matrix A has entries that are secret shared over the field Fp, and we are going to sample a lower and upper triangular matrix at random, where this L is actually unitriangular. So it has ones on its diagonal. Then we're going to compute the product of this L and U, which we call R, and let D be the determinant of R. And we can compute that determinant immediately from the diagonal elements of U. Now we're going to compute the product of R and A and reveal this product. So we make the product public. And this R then acts as a blinding matrix for A. Now in the clear, we can compute the adjugate and the determinant of A, for example, with the Bareis algorithm. And then remove the blinding and go back to the secret shared world by multiplying from the right R and the inverse of the determinant to get the adjugate of A, and the determinant of A is equal to the determinant of RA times the inverse of D. And if you would compare this algorithm to, or this protocol to the one from Kramer and Damgaard, making this L unitriangular actually somewhat simplifies the proof, because in their protocol they do not use a unitriangular matrix. And of course they don't keep this determinant and adjugate separate. Yeah, this gives you a constant rounds or constant rounds protocol with squared order n squared local work. And here this n squared assumes that I have a cheap inner product, as Shamir has a cheap inner product. So that if I do a length n, or have vectors of length n, and I compute the inner product, that's as expensive as just computing one multiplication. Because I can compute all these multiplications in parallel, which is local work, and I don't count it, and I just have one resharing, so one interaction with the other players. All right, now I want to show this protocol, how you can implement this in MPyC. So I'm going to switch back to my mirror screen, to the browser. Make it a bit bigger here. And I'm not going line by line through this implementation, but I just want to see that if you are working on such a protocol, it's quite easy to implement it in this MPyC and check whether you didn't forget something. So here is just an implementation in plain Python of the Bareis algorithm. And this computation is one that happens on public data, because it's run on this non-secure part of the opened matrix. So, well, we believe that that is a correct implementation of Bareis. Here I wrote a wrapper to be able to use some NumPy functions. For example, for the part where we have to sample the random matrix, we are first creating this lower and upper triangular matrix, and NumPy provides these handy functions for arranging data at a certain way in a matrix. And I can reuse that actually for my secret matrices, because NumPy has a parameter where you can specify what the element type of the matrices or the objects should be. So this is another example of where an MPC framework that is implemented as a library has a flexible way of interacting with the features of the host language, which I make use of here. So here, I create a random vector. I divide, or I compute the inverse of the product of the diagonal elements of the matrix U. And here this MPC.prod does a product tree. So it's a logarithmic depth product over a list. So it's a fold over a list that is run in parallel. Here I actually use the multiplication operator from NumPy, and I apply that to the secret matrices. But actually in MPyC there is now also a matrix product operator. Anyway, this function gives me the blinding matrix R and this inverted determinant of the matrix. And then here, this is the actual function, which is a coroutine. And MPyC makes use of async IO, which is the asynchronous API of Python. And in async IO, you have function definitions that use the keyword async def. And there's also a decorator here, which is from MPyC that does some bookkeeping. So anyway, here's the top level script. I have a matrix. I secret share the elements, and then I run the protocol, and I open the result. And here, well, we get the output. And again, this is just to demonstrate that in a few lines of code, you can quickly implement the protocol and see whether things work out. Questions about this part?
Does MPyC look at A and decide how big the modulus needs to be, and
The
do
question
that
is,
automatically, or did you have to be careful when you split?
The question is, how does MPyC know the modulus? Well, there's a default modulus that it picks if you don't specify one. And in this case, I just kept that default choice because it allows me to compute up to 32 bits, or even bigger actually, but only the comparisons are limited to 32 bits. But if I need a bigger modulus, I can just specify that. So if you would have an actual application, you would look at or find an upper bound for the elements of A, and then apply Hadamard algorithm, and then or the Hadamard bound, and based on that set the correct prime, or set the bit length of the prime.
Okay, got it.
Okay, we have 15 minutes left. So then I want to continue about comparison. Yeah. So in the 80s, there was Andrew Yao who proposed the millionaires problem, and today you would call it the billionaires problem. And they want to know who is the richest, without revealing their account statements. But let's assume that these billionaires are extremely paranoid, and they don't want to run a two-party MPC protocol because they are afraid that somebody has a quantum computer in his backyard and attacks this protocol. So let's go to a three-party protocol where MPC can actually offer a quantum-resistant solution. And here, Andy Yao, who's probably not a billionaire, maybe he's a millionaire, I'm not sure, but he just runs as a third party, as a helper party. So he is involved in the protocol, but he does not provide any inputs, and he does not see any output, but he's just there as a helper party. And Warren Buffett and Bill Gates, they essentially want to do a comparison. So you have two inputs, A and B. You can subtract them and then determine the sign of that difference. That would be a comparison. And then, of course, you can distinguish between, the proper signum function, where you have also a zero here as output. This is a ternary output, or you have the greater or equal than zero function, which has a binary output. And in this part of the talk, I want to evaluate the sign using quadratic reciprocity. So if you carefully pick a prime, then you could have the situation where the Legendre symbol coincides with the sign of a number over a certain range around zero, where this range, minus d up to plus d, can be of size order L, where L is the bit length of the prime. And this idea goes back to Feige from 94, that used this trick to compute the sign of a number in an interval -2 to +2 in F7. And more recently by Yu this was explored for much bigger primes and see how you can build a comparison protocol from that. And that's on ePrint, that paper by you. Well, for example, for the prime 311, which is, by the way, a Bloom prime, and because it's a Bloom prime, -1 is not a square, so we have nice odd symmetry around 0 in the Legendre symbols. And here up to 10, or up to 11, up to and including 10, we have this correspondence between the Legendre symbol and the sign of the numbers. And because of this Bloom property, things look the same or mirrored at the negative part. Yeah, so this could be viewed as a way of determining the sign of numbers in a small range. And we can use this idea also in MPyC, or in MPC, I should say, if we can efficiently evaluate securely the Legendre symbol. And the complete multiplicativity of the Legendre symbol admits the following folklore protocol for computing it. So first, in an offline phase, we would compute a random field element together with its sign. And then in the online phase, the x here is the input. We multiply it by this random field element. So we blind it, then we can open this product. And we then can compute the Legendre symbol of that C as a clear text computation and compute it with the secret shared sign of that pair to get the result. You can do this in one communication round. There's one caveat here, namely that we cannot use this to evaluate 0, because then we would kill here immediately the product, and the adversary can see that we input 0 there. But let's ignore this for this talk. We have written a paper, and of course there we do care about it, but here let's just assume as if we can compute the Legendre symbol securely and not worry about this 0 that we actually have to circumvent.
Is it really the case that the prime does not have to be enormous to have this property that you need? I would expect if you want the interval to be non-trivial, the prime would be ridiculously large.
Yeah, there's a question here whether the prime has to be ridiculously large or to end up with a usable or reasonable interval. And yeah, there is indeed this log p. But I do have a table at the end of the talk that shows some practical values. And indeed, you won't have an extremely large comparison range or sign evaluation range, but still it could be, for certain applications, could be interesting. But let's come back to that later. Anyway, this is basically the idea of Feige et al. And this U paper. Now the question is, how can we increase the range? Of course, we can just pick a bigger prime, and then we will get a somewhat bigger range. But the question that we pose in this work is whether we can get a bigger range while we keep the bit length of the prime fixed. And why would we be interested in that? Well, there's a cost associated to increasing a prime. Well, in this work, what we do, if we look again at this 311 prime, then if you look at this error, so to speak, then well, the sign function is not such an interesting function, right? Or there's not much happening here. It's just a constant line. Only some interesting stuff happens around 0 where you have the transition. But here you could actually peek at your neighbors and do a majority vote and repair that error. So you take the sum of the Legendre symbols of your neighbors and yourself, then you get in a range of -3 plus 3. And then you would have to compute the sign of this y of x. And you can do that with yet another invocation of the Legendre protocol. or you could use a polynomial to find that sign. Well, in this case, we now have we look at one neighbor at each side. So let's say k equals 1, and we have a window length of length 3 in this example, so 2k plus 1. But we can generalize that and have the following definition where we define the k range of p. Well, where you take a bigger k, and hence a bigger window, and you call d the largest integer such that you still have correctness for your for this method. And we set dkp to 0 if you cannot find such a d. And with this definition, we can now go to the table of some examples. Here, the first column gives you the d0 of p, which is actually the Feige style range. And if you have a window length of 3, then you get this d1 of p. And if you have a window length of 5, so you look at 2 neighbors on the left and the right, you've got this d2 of p. And if we look, for example, here at a 32 bits prime, where we get the range of 96, here if we look at a 32-bit prime, we get a threefold improvement. And here you have already an 8-bit range plus a sign, so essentially 9 bits. So there could be applications where you are interested in working with this low or medium range numbers. And if we go to k equals 2, for 32 bits, we would actually be here, is 458. So compared to d0, that's almost a 5-fold increase in the range. Well, I have a question.
But then you're also paying a factor of 5 for computing 5 Legendre symbols, right? Or is there any trade-offs? I mean, can you compute 5 Legendre symbols cheaper than 5 single ones?
There's a question that you also have to increase the local work. Yeah, that's true. That's a trade-off. You still need to compute those Legendre symbols. I'm not aware of a method to compute them all together in a more clever way. Yeah, but indeed, you do have to do more local work. But one example where that could pay off is that say you are on an embedded platform and you also have memory restrictions, so you don't want your numbers to be too big because you have to store them. Then maybe you can exchange space for time there.
Did you also look at different primes, using, say, 3 primes and then taking the majority vote?
Another question here is whether we looked at taking different primes and then take a majority vote between the results within those prime fields. The answer is no, we did not. I think you can do that. It would be an interesting direction to look into. But also with, say the setting in mind where we usually work over a single prime field.
You'd have to reshare.
Yeah, you would have to do things between those prime fields. So there would probably be modulus conversions be involved, which are not for free. So we applied this comparison method to the evaluation of neural networks. And this is a multi-layer perceptron from a paper from 2016 from Cour-Barriot et al., which is for MNIST. So here we have this handwritten digit, and we want to recognize the digit, and we want to do this or evaluate this in multi-party computation. So how the multi-layer perceptron works is well, it's a bit small here, but there's a matrix of parameters, and the elements of this matrix are -1 or +1, so binary in some sense. And you do a matrix vector product where the vector x0 is actually the image that has been flattened to a vector. And then there's also a bias vector that you add there. And here the nonlinearity is taking the sign, so that maps well with our work here. And then you do these matrix vector products and taking signs through a couple of layers, and at some point you end up with a vector of length 10, where each entry gives you an estimate of say the probability that the digit is that particular number. So the probability for that it's a 0, probability for 1, etc. And then you could take an arc max. So we have implemented this in MPyC and report on the results in an upcoming paper. Okay, this concludes my talk. Thank you very much, and I think I stayed within an hour. Thank you.
Any further questions from the room?
So I have a question about the linear algebra evaluation. So you sampled some random matrices L and U, and then you publish the L times U basically times the secret shared matrix. So can you prove that it doesn't leak any information about the secret matrix?
There's a question about the linear algebra protocol, whether the blinding operation and then opening the blinded matrix does not leak sensitive information. Well, the answer is yes, there is a proof, and the proof largely follows the proof from Kramer-Damgaard, but it even simplifies a bit because we've got now this unitriangular structure on L. Mm-hmm. And then it's as easy as showing that there is a bijection, so that things are fine.
Okay, and also, so for the determinant evaluation, so you sometimes need to divide by the determinant, which is because of you sampled those random matrices kind of uniformly randomly. The determinant can be like a random number in the finite field, right? So it's not necessarily smaller than root p. So in that case, can you still do the rational reconstruction when the denominator can be arbitrary?
There's a question about the determinant and dividing out this determinant, and also in relation to rational reconstruction. First thing to mention is that we do not use rational reconstruction because we circumvent it by keeping the adjugate and determinant separate. So we never perform a division that is non-exact. Mm-hmm. Maybe that already answers your question.
Yeah.
But otherwise, let's take it offline.
Okay. Anything further? Okay.
Thank you very much.